Okay, class. This video is to give you a little instruction, a little help in writing proofs in this class. The proofs in this class are very algebraic. I mean, it's just linear algebra. You're doing manipulations like you've been trained to do for many years, like using rules and properties. Except the property, you will be learning new properties because you're going to be working with operations of vectors and matrices. You'll have different kinds of operations. So you'll be learning new ones. So you'll be using new ones. But they should all have a pretty similar feel to what you've been doing when you're in like solving equations, when you're trying to move stuff around and simplify things and stuff like that. So I'm going to give you a few rules of thumb, and I'm going to use some of these, the examples here. Some of these are from your homework to illustrate. So first thing is try exploring. Especially if you don't understand yet, you don't really understand what the question is asking, or if you don't have a good feel for it, try exploring. And a good one to do some exploring is number 60 right here. So suppose we know that u dot v equals u dot w. Does it follow that v equals w? If it does, give a proof that's valid in Rn. Otherwise, give a counterexample. So this isn't really a good problem for you to start reasoning abstractly about it and maybe using properties. It's hard for me to, so I wouldn't expect you guys to. But one thing that we could do is just start with an example. Okay, let me just pick a very simple vector, 1, 1, 1. Can I find two different dot products two different vectors that have dot products of 0? So you could try that, and like here's an easy one. 1, a minus 1, 0. Okay, that dot product equals 0. Can you find another one? Yeah, well, I'll let you find another one, but you certainly can. So this is an example where forget about the u's and the v's. It's a nice problem to just start pulling out some specifics and get a feel for it. You also have other tools. You could pick a vector and say, well, let me see what kind of things I end up with if I pick a general vector, a and b. It's supposed to be an a. So a dot b, if I know that has to equal 0, then I get a plus b has to equal 0. So that says, well, a has to equal a negative b. This alone tells me, hey, there's many choices I could have for this. Any choice I get for a tells me what I get for b. If I plug in a equals 1, then b equals a minus 1. If I pick a equals pi, b equals a negative pi. So you also have algebraic tools to help you out doing some exploring. So that's number 1. 2, write down or list what you know. And these are often definitions. We use definitions a lot. We always have to go back to definitions. Theorems or properties. In this book, a lot of the properties are listed in as theorems. But so write down or list the things that you know. So this could be the things you're trying to prove. Or the things you're starting with. Both of those things. So let's look at which problem was that? I know I had an example here. 68. There we go. Okay. Prove that if u is orthogonal to both v and w, then u is orthogonal to v and w. Okay, so u is orthogonal to v and w. What does it mean for u to be orthogonal to v? Well, intuitively, they mean it's perpendicular, right? They intersect at 90 degrees. Okay, I could list that, so I know that. What else do I know about that? If you look back in the book, it defines it actually not as the intersection, but as it defines it in terms of a dot product. So The definition, it says two vectors u and v in Rn are orthogonal to each other if u dot v equals 0. So already you can start being like, okay, if they're orthogonal, then I already know u dot v has to equal 0. And I already know that u dot w has to equal 0. Okay? So those are some things that they give me. I already know that. What am I trying to prove? So looking at the end, trying to start at the end, what do I know about that? U is orthogonal to v plus w. What would we have to show, or what does that mean? Well, that means u dot v plus w has to equal 0. So just trying to write down what, going back to definitions about what those things mean, gets you something. Or using theorems, you might look up the theorems and just start listing all the things you know about what you're proving or what they've given you. And already this much down here starts to get you a lot, because we already know this, and this is what we're trying to show. And so we might try starting here and seeing if we can use those somehow. That gives another trick. Try working backwards. When you're working with equalities, then or equations, all the rules that we do work both ways. So you can just start with this equation and try to show the right side is equal to 0. And the way you do this in this case is, hey, I know how to work with dot products. Well, I hope you're learning how to work with dot products. Then you can go back and look at the properties, and you can be like, oh, yeah, there's something about the distributive property. So I can rewrite that as u dot v plus u dot w equals 0, and then you know that this is 0 and this is 0 by the definition of orthogonal and what they gave us. So therefore we showed that u plus v plus w is actually equal to 0. So what I should have started with is just, I'm not going to start with the 0 over there. Well, that's what we want to show, but I could start with just u plus u times v plus w equals u dot v plus u dot w. This is by the, you can list the property by the distributive property or by whatever theorem it is. And then 0 dot 0, sorry, that's equals 0 plus 0. You can say it's by the givens, we're already given that, equals 0. So we showed that equals that. So that's the kind of stuff I expect you to be doing. That's very similar, or very typical of what you'll be doing in these classes. And then look for, you're going to look for manipulations you can do. So in the same way that we looked for like the use of these properties, look for manipulations, because almost all of our proofs are just algebraic manipulations using new properties and new definitions. So a nice example of working backwards is problem number, is this one right here, 63. So show that u dot v equals this thing. Well, it seems like it's a lot easier to start with this side and start expounding it and simplifying and try to get that than it is to try to like add stuff to this and try to get that. So yeah, start with this and start simplifying so you can show that this is equal to u dot v. So it's a little bit of working backwards there. And then one other trick that might be helpful, I used this in the other video that I posted today with showing that the dot product, how the dot product is related to the cosine, where I derived that, is instead of working with vectors u and v, I forgot to mark all these as vectors. You should be careful about that. You guys can call me out in class on this, because I need to be careful about that too. So instead of using vectors, vector notation like this, some of you will be a lot more comfortable to write out u and v as components. So So let's call u1, u2, dot, 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 to un. And v is v1, v2, dot, 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 to vn. And then when you start working, like if you have an expression like 1/4 u minus v, those are vectors, squared, then you can start translating those into these individual things. Well, that means 1/4. I'm going to take u1 minus u minus v is going to be u1 minus v1, and then the norm I'm going to square each of those. u2 minus v2 squared, u3 minus v3 squared, dot, 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 un minus vn squared. Okay, and then if I didn't have this squared, I'd take the square root, but I squared this, so those cancel each other out. And so now I'm just working with these things, and you guys are generally more comfortable working with expressions like this rather than expressions with vectors. Most proofs you don't have to do this, but sometimes you do. Okay, so that's a little bit of help there with your with doing proofs. Oh, here's another example, 69. Prove that u is orthogonal to v minus the projection of v onto u. Okay, well this thing, I don't know how to work with that. So that doesn't help me very much, especially if I'm trying to do manipulations, algebraic manipulations. So what am I going to do? I'm going to go find the definition of that, see what that means, and especially if there's a formula for that. And there is a formula for that. So I can start with, projection of v onto u, that's v dot u over u dot u all times u. So I can replace that thing, and then I can start off, prove that u is orthogonal, and a definition of orthogonal, so I'm going back to the definition here. I need to show that u dot this much equals 0. So u vector dot v vector minus that, I have to show that equals 0. So do manipulations to that, dot, 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 and eventually show that equals 0. So I hope this helps. There are some other resources on a Learning Suite page on Learning Suite. It's on a content page on Learning Suite, so you can go look at those also. Okay, thanks and good luck.